Hello, everyone. We're going to continue our discussion of integrating rational functions. In class, we talked about using partial fractions to break down a complicated rational function into simpler pieces. So if the denominator can be factored, then we know how to solve the problem. Unfortunately, this type of factoring is not always possible, so we have some rational functions where the denominator does not factor. Here's one example. If you use the quadratic formula, then you'll see that the roots of this equation are actually complex numbers. And so it's not possible to factor it unless we want to use the number I. And we're not going to do that in this class. It's still possible to integrate a function that has a denominator like this, but we're going to need a new approach. Before we get into the details, I want to review some ideas from algebra. First one is adding 0. So for any function, I can always add 0 without changing its value, and we're going to use this idea in a slightly different form. So here I added plus 1 and minus 1 to my function. The overall effect is just adding 0, and so I haven't changed its value. Another similar idea that we're going to use is multiplying a function by 1. If I do something like this, I haven't changed the value of the function. And again, it's going to be most useful to us in an alternate form. Here I wrote 1 as 2 over 2. And for my next step, I'm going to distribute, but I'm only going to distribute on top of the fraction. So here I've multiplied that 2 by x plus 1. The 2 on the bottom stays out front, so I have a constant 1/2. The final idea that I want to review is completing the square. So if we have a quadratic function that doesn't factor, this is how we do it. I'm going to take my quadratic and rewrite it in the form that you see on the right-hand side. X plus k squared plus h. And in this expression, h and k are both constants. The name of this process, completing the square, well, we have a function being squared. And so we would call that piece of our problem a perfect square. This is something that you learned how to do in algebra class. You might have seen it in a slightly different form. But we're going to take what we have on the left and rewrite the pieces. The first step, I'm going to group the x squared term and the x term. So I put some parentheses around those. Now I'm going to think about what constant I need to add in order to make the function in parentheses a perfect square. It turns out that inside the parentheses, I need to add 1. And I found that I took the coefficient of x, which is 2. I divided that number by 2, so 2 over 2 is 1. And then I square the result. 1 squared is 1. So my final answer is 1. I add 1 inside the parentheses, and then I cancel by subtracting 1 outside. The net effect of doing this is just adding 0. Next step, I simplified a bit. I combined those two constants on the end. And finally, I wrote my problem in factored form. So I'm done completing the square. I have the form of my function that I need. I want to go on and see how we would apply this idea to integration. So we're going to do the integral. It has that denominator that doesn't factor. And our first step in this problem, it's what we already did. We're going to complete the square. So I wrote the denominator in its correct form. And the point of doing this is that we set up a really nice u substitution on our next step. I've laid that out there. When I plug in this u substitution, here's the expression that I get. Now this should look familiar to you. We were talking about it in our previous classes. I see an expression of the form u squared plus k squared. K is equal to 2, and that implies a trig substitution. For this particular pattern, I'm going to use the substitution u equals 2 tangent theta. The good thing about this is it's actually an easy trig sub problem. It's not as complicated as some of the ones we've seen before. I plugged in that substitution, replacing u with the appropriate trig functions. The rest of this is familiar, so on the bottom I'm applying a Pythagorean identity, and then we simplify by canceling the common factors. I'm left with the integral of 1/2, and of course that's 1/2 theta plus c. We're done with the integration step. The next thing we need to do is reverse our substitution. And we actually had 2 substitution steps in this problem. To reverse the first one, well, we defined u equals 2 tangent theta. That implies that theta is the inverse tangent of u over 2. So I plug that into my answer and I get the following expression. We finish off by reversing our first substitution. So initially we defined u equal to x plus 1. I put that in my function on the last step. And that's it. We're done with our first example. Here's kind of a summary of what we came up with. So when we have a problem like this, the basic ideas are, number 1, we're going to try to factor the denominator. If we can, then we solve it by partial fractions. But 2, it's not always possible to factor, and in that case, our approach is going to be completing the square. Okay, that takes care of our first example. I want to look at another similar problem. So here we have x plus 2 over x squared minus 2x plus 3. The difference between this one and our last example, I now have x in the denominator. We're going to start the same way. We'll try to factor the denominator. This is another example where it doesn't factor. You can check it out. And so instead, we're going to take the following approach. First, notice that the derivative of the denominator is 2x minus 2. So I want to rewrite my problem in the following form. We want 2x minus 2 on top, and that's going to set up a u substitution that lets us take care of at least part of this problem. All right, let's see how we rewrite this rational function. Remember, we want to see 2x minus 2 on the top of our fraction. So I'm going to start by getting a 2x up there. I do that using the idea of multiplying by 1. So I multiplied my fraction by 2 over 2. Now I'm going to distribute in the numerator only. And I get the following expression. Notice that the top of my rational function contains a 2x. Okay, the next step is to get the minus 2 that we want in the numerator. And we're going to do this by adding 0. So I set that up here. Notice that overall I added minus 2 plus 2. And the net effect of doing that is just adding 0. The minus 2 and the plus 2 cancel. There I simplified, so I added the plus 2 and plus 4 on the end of my expression. And then I'm going to split that up into 2 pieces. The first fraction in parentheses has 2x minus 2. That's the derivative that we were looking for. And then the remaining constant, that gets its own fraction. Then I distributed my 1/2 through the parentheses. I'm finished with my algebra step. Now I'm going to go back to my original integral. And we're going to use the work that we just did to split this integral up into 2 pieces. Each of these 2 pieces is something that we've done in our class before, so let's take a look at the integrals on the right-hand side separately. Here I set up the first one. So we want to integrate 2x minus 2 over x squared minus 2x plus 3. The work that we did set up the following u substitution. I let u be equal to the denominator, and then all of that algebra gave us the derivative in the numerator. Well, we carry out that substitution and we get this expression that's familiar. Its integral is a log. Last step, we reverse the substitution, and now we have the solution that we need for the first integral in our answer. Now I'm going to go on to the second integral. And if you notice, this is a lot like the first example that we had. So we have a constant in the numerator, we have an irreducible quadratic in the denominator. The idea that I'm going to use is to complete the square to set up the inverse tangent substitution. Okay, here I'm laying out the steps of completing the square. I take the coefficient of x, divide by 2, and square it. So I add plus 1 in the parentheses. I cancel by subtracting 1 outside the parentheses. All right, there's the form that we need. So we're going to go back to our integral, rewrite it using the form from completing the square. Just like the last example, that sets up a u substitution. So I let u be equal to x minus 1. I plug that in, and I have an integral where I'm ready to use a trig sub. For this particular problem, I'm going to use u equal to root 2 tangent theta. Take the pieces of this substitution and plug it in. You get the following expression. I'm going to simplify that denominator. We use a Pythagorean identity to do that. And when I cancel the common factors, I'm left with that integral right there. We evaluate it and get 3 root 2 theta plus c. I finish off this integral by reversing the substitution. Again, we had 2 substitution steps. So for the first one, I use theta equals inverse tangent of u over root 2. Plug that into our answer and we get the following expression. And I finish off by reversing the first substitution. Okay, so now we're going to go back to our original problem. Remember, we took our first statement of the integral and we split it up into 2 pieces. We did it in such a way that each of the pieces were something that we knew how to integrate. So I plugged in our results from the integration step there. And I finished up my problem by doing a little simplification. Okay, that's it. So I attached a sheet with a couple problems that I would like you to try. Please write those up and give them to me at the beginning of our next class.